Yeah, sure. Okay. Hello again, everyone. I think I already expressed that I'm very excited about hacking. But I wanted to say just like 2 minutes, a few words about what uh, sort of hack sessions are all about and what, some things to think about and what I hope that we get out of it. And just a big thanks to Daniela Huppenkutten who provided some slides because she's thought about this more than anyone else that I know. So first, I just want to define what hack means in a few different ways. And basically, the main thing is that this is an opportunity uh, to work on some small project that can be, that has a very clear goal that can be completed in the allocated time, which is, potentially by the end of today or by the end of the week. And so you should think about the scope of the projects that you're working on. But this is, and in particular, you might want to simplify your approach or use this as an opportunity to try some, very hacky solution for the types of problems that you want to solve. This is your time to give that a shot. But also, the idea is that you want to take this as an opportunity to try something new that you maybe haven't had the right time to do before. But it's also worth remembering that when you're trying something new, that it might not work, and that's okay. That's part of the point of this, and that's one of the things, there will probably be lots of failing that happens, and that's part of this entire process. So like I said, you should try something new. And in particular, you should, be bold about what you choose to do. Everyone in this room has expertise, and that expertise is in different directions. And hopefully, together, we can, benefit from each other's expertise to succeed at something that we try. And it'll be most productive if we make sure that when we're working in groups, that we really listen to each other and take advantage of the different expertise that exists within the group. And so make sure that you create a welcoming environment within your group so that we can really all benefit from that kind of thing. Jennifer already mentioned this. We're going to start with introductions after the talks today, and this is really important because I think a lot of people in this room know each other, but there are, some new people, some new faces, some people who don't work on microlensing at all, and it's a good chance to get to know each other, but also to sort of pitch what you want to work on, and so fill out the add a slide to the slide deck. If you haven't done that already. And the link should have gone out, but if you need the link, you can ask me and I can send it to you as well. And Rodrigo asked me to mention that there's a space for putting in your GitHub username that has recently been added. And so please go in and edit the slides and add that if you can. Logistically, this entire floor is ours, so you can go into all the corners, use the whiteboards, use the chalkboards, hang out in here, whatever you want to do. Take advantage of it. And I was just going to say, we're going to try out using the GitHub organization as there's a discussion board there. And so if you want to send messages to people in this room, you can post them to this this discussion board. We'll give that a try. Absolutely. Totally. Yeah, will do. And I'll include the slideshow link in that as well. And then the last thing I wanted to mention is that we're going to have the opportunity to do breakouts. And basically the idea with a breakout is that there might be some topic that is of interest to many people in the room, and there might be various levels of expertise in those things. And so a breakout is an opportunity to have a sort of group discussion about a topic that's isn't necessarily one of the hacks, but something that people might be interested in. For now, I'd suggest that if you're interested in pitching a breakout topic, you put it on this discussion board, and we'll try to allocate times and places for those things to happen. I think that's all I wanted to say. So yeah, just make sure you add your slides and have a great time and make the most of the space that we have here. Thank you.
Thank you, Dan. Anybody got any questions about the overall format so far? No? All good? In that case, I will invite David Bennett up to talk about the unsolved problems in microlensing.
Okay. Yeah, so I'm going to talk about a couple of unsolved problems in microlensing, which were the two problems that I thought were the sort of most pressing. One is that the current way we deal with degenerate models is not really sufficient for a statistical analysis, and there's lots of cases where we get two or more light curve models that fit the data. And to do a statistical analysis to determine the properties of planetary systems, we pretty much need to include these degenerate models. We can't just throw them out. And so we need to have a good way of including them in statistical analysis. There seem to be pretty good ways for doing this, but we're not currently using them. So implementing those would be a good idea. And then triple lens model parameter search. This is well, I'll explain a couple of things about this, but the main problem is a much larger parameter space, and sometimes the parameter space seems to be too large to use the sort of brute force methods that we've been using. Another problem is that in some cases the calculations are very time consuming, and that of course makes a brute force search much more difficult. So it would be good to be able to speed up those calculations and then look more carefully at how to find solutions. Okay, so the degenerate models. So there's three categories. Intrinsic light curve degeneracies. These persist even with high precision data, and so this is like the close wide degeneracy that everyone knows about. There's a few other ones that people have pointed out. There's ones due to low photometric signal to noise, and those are going to persist with W first, even though, for the sort of events we're observing now, W first, we see them with much higher signal to noise, but they're fainter stars than the ones we're observing, and so W first will have those as well. And then there's others due to poor light curve coverage, and so this will be kind of rare with W first data, except at sort of the beginning or the end of the season, or when the spacecraft goes into safe mode or whatever. So currently, so Bayesian analysis is well suited for these degenerate models because your measurement can have degenerate interpretations, and you just multiply that by the prior and proceed. What we've often done is just wait by this delta chi-squared between the do best fit solutions. That works in some cases, but in general, it's not very good. So as Clement mentioned earlier, it does depend a bit on the volume of parameter space, and it depends a bit on the prior, because that tells you how to integrate over the parameter space. Markov chain Monte Carlo could give the correct weighting, but the problem is that you can't often, for a normal Markov chain sampler, you can't explore all the different solutions. Okay, so this is an example from the MOA analysis of 30 planets that was published a few years ago, and so this shows the sensitivity curve, but then there's a number of these events with the close wide degeneracies. Okay, and these are pretty common. They occur quite often in high magnification events, and those are the most sensitive events to planets, and so we don't want to throw those away. And then there's also this event, which is one which actually is another degeneracy between planetary and stellar binary models. And so we need to make sure we have a good way of handling these degeneracies. So this is the example of the close wide degeneracy from that previous sample. This is MOA 2007 bulge 400. And it's basically got a close wide degeneracy that differ in separation by almost a factor of 10. And but if you look at the plot of the likelihood surface here for the close and wide models, they almost are the same. And so this is a case where just that weighting by the delta chi-squared is probably okay. But then these ones that from the MOA 9-year analysis, these are ones that that Yuki showed. So this one is the the degeneracy between a planetary model and a non-planetary model for an event which is basically densely sampled but only from one site. And so there's a lot of problems with missing data. And so this is, to include this in a statistical analysis, we need a good way of weighting these different solutions. This is another one that Iono showed yesterday, and here, there's also the problem with the lack of coverage, and an event is fairly faint and also fairly short. So those are a couple examples. This is an example where from more than a decade ago, on a poorly sampled event by Moe and Ogle. This one, so here's what the light curves look like and the caustic features for each of these degenerate models. There's actually one of them which formally gives the best fit is actually excluded. It's basically, there's so few points on the deviation that if you put caustics going between them, they you can adjust the microlensing parameters to get every point to fit exactly on the deviation. But this one has an unreasonably large implied lens mass. And so if you plot this is from a Markov chain, actually a combination of Markov chains. There's these solutions here, which are these caustic crossing solutions. And they're pretty different from these other ones, which are all pretty much just cusp approach solutions. The volume in parameter space seems to be very different. And so you might argue that these should have very low priority if you're doing a Markov chain over these, and you can jump back between the various solutions. And in fact, I once got into an argument with Andy Gould about this, and he argued just this point that these solutions would be very improbable. Currently, they're just favored by an analysis of VLT NACO data, which indicates it looks like evidence for the lens star, and these solutions all imply that the lens star is less than 0.03 solar masses, so we wouldn't be able to see that. Okay. But a more important degeneracy is this planetary stellar binary degeneracy. And this is from a paper by Hans group, Che et al. 2012. This is the one event from the MOA statistical analysis that had the degeneracy between planetary and binary solutions. And so they analyzed this event first. And so basically there's approach of two cusps. If you're not too close to the cusps, then you can get light curves that look very similar, and it could be these two cusps of the central caustic of a planetary event, or these two cusps of a stellar binary. Okay, and so this one is particularly important to sample. This is also from the Che et al. Paper, and then just showing the light curve. So there's pretty good coverage here. There's a bit of a gap up there, but anyway, this one, even though the data could probably be a little better, this one is a case where, the degeneracy exists because of, a real degeneracy in the light curve shapes. And, if you had better photometry, you might have to move a larger U0 to get the same kind of degeneracy, but you're not going to avoid it with better data. In general, you're not going to. And just to show, this is from Markov chains centered around the four solutions. So here's the two planetary solutions, close and wide, and these are basically mirror images of each other, and they look almost the same if you plot the absolute, plotted as a function of absolute value of log s. The close and wide solutions don't look exactly the same because there isn't really quite the same symmetry there. And we don't think that the treatment of this solution actually has much effect on the Suzuki 2016 results. And this is largely because the delta chi-squared here is 19.8, which is a little bit marginal. But if we say that we're, got the delta chi-squared off by a factor of 2 or even 4, it doesn't make a huge effect in the final results. And so the way we dealt with this in this paper is just to weight by the delta chi-squared of the best fit value of the different solutions without really taking into account the integral over those solutions. And this only works because it's only one event. It does have a moderately strong preference for the planetary model, and but in general, we don't want to have to do this again. Okay, so we had some discussion about this before, and Clement has been working on this a little bit. But I think this paper that Eric Ford mentioned yesterday, describing the mixed Markov chain Monte Carlo, is kind of the simplest way to do this, and this just mostly involves adding to your jump function to take a new step in a Markov chain, a possibility of switching between the locations that you've already found for the different solutions. So, the thing, you have to identify the minima in advance, but this is generally what we do, and this is sort of not the part of the problem that we're missing. So this seems pretty straightforward. This repelling attractive metropolis method by Tak et al. I'm guessing that it's not very well suited for things like this. For things like this, where the minima are very well localized and widely separated in parameter space. And of course, I'm only showing 2 dimensions here. They're widely separated in a bunch of other parameters as well. And so any kind of Markov chain that's trying to sample the whole parameter space is likely not to be very efficient. And then, so I don't know so much about these other ones. The differential evolution Markov chain and affine invariant Markov chain have been described. Also, some people have tried multinest, but a lot of people have suggested that these aren't such good solutions, and they don't seem to be designed specifically for this problem, whereas this one does. So as far as I know, no one's actually implemented that, but I think that would be a good thing to try during the Hack Week, to try and get a simple implementation of this so we can start testing it. Okay, so now I'm going to talk about, triple lens modeling, but first I wanted to mention binary lens modeling. So basically, we've done pretty well with brute force grid searches. More than a decade ago, there was a little bit of an issue with very slow calculations for things like high magnification events, but that's pretty much been solved in a number of different ways. For some events, it's very, very helpful to switch to coordinates that are based on caustic crossing times, because often you can just read those right off the light curve, and so it makes it much easier to optimize the parameters. And basically, I think the current methods we have for analyzing binary lensing events are adequate for what we need for WFIRST, for basically getting reasonable binary lens models for all the binary events. Okay, and this is an example. This is the first one that actually showed a grid search in a paper. This is Ogle 2005-169. It's the second low mass planet found by microlensing, and so this is the result of their grid search. There's a bit of ambiguity because there's very little data before the peak, and then great coverage right after the peak, and so that leaves some uncertainty on the angle that the caustic has crossed. And so this is the best fit here from the initial model, but we actually got a confirmation of this from HST follow-up observations, and that actually indicates that the correct model is here with a different angle that we thought. That means that the predicted lens source separation velocity is different than it would have been for this model. And so, this method is used for a lot of different events with some variations, but it works pretty well. And generally, whenever there's a binary event, multiple people model it and get pretty much the same answer. There's a few special cases where some methods don't sample quite all the same models, but now I'm going to talk about the triple lenses. And so the first to talk about is one star with two planets, and that's generally easier than the cases that involve more than one star. And this is just because usually it's a case when you have planetary light curve, a planetary signal, it doesn't affect that much of the light curve. So you can approximate a lot of the light curve as a single lens. Okay. And also, and this is related to the fact that then, you can even eyeball a lot of these light curves and identify the individual planetary signals, even at high magnification, when there's some potential for them overlapping. So you can get a good idea of what the solution is without having to search a huge parameter space. Okay, so this is the first triple lens event published, Ogle 2006, Bulge 109, and so this was monitored in real time by Scott, who actually managed to predict this peak number 5 or feature number 5, after the first three peaks, first three features that occurred, and then there was a big surprise that there was a peak number 4, and that's the 4 of the 5 peaks or features are due to the lower mass planet, the Saturn, and this feature is due to the Jupiter, and it's due to the fact that the Saturn is quite close to the Einstein radius, whereas the Jupiter is further away. This is the caustic configuration. There's a parallax signal here, and the caustic's changing because, and in fact, between the feature 1 and feature 5, you need to include the change in the caustic shape, because otherwise you can't come close enough to this feature 5 without getting a bigger signal at the peak. So this is one where it wasn't that difficult to figure out the solution. There was a little issue with including the orbital motion because we hadn't been previously doing that very much, but we didn't have a problem with the method of finding the right model. This is Ogle 2012 0026, a high magnification event, and you can see the two sort of clear features. This is first modeled by Han. There's a degeneracy here that just has to do with the close-wide degeneracy of the two different planets, and when you add parallax, there's an additional degeneracy there. Okay, then the third two-planet event that's been published was a Suzuki et al. 2018 paper. There's this clear planet here in both the Moe and Ogle data, and then there's a little bump on the light curve here that's most likely due to a planet, although the exclusion of the binary source model is a little bit marginal. But that's a factor of the data, and you can't really do modeling is not a problem there. Okay, so this is the first of the unsolved events, and this is one of the earliest planetary events. It's been remained unsolved for a very long time, and for much of the disappointment of the amateur astronomer who got the data on this caustic crossing. And we made some effort modeling this, and in fact, I did an early model of just a binary lens that had a peak out here, and this inspired Udalski to go check the Ogle data, and he found another observation that just happened to be higher. It was a little different than my original model had, but this made us think that maybe we were on the right track, that there was an early caustic crossing here. And so that is a caustic crossing here, but it's 30 days away from this, okay? And this is a similar case to that Ogle 06109 event, where because there's 30 days between the first feature and the last feature, orbital motion is important. And so we include orbital motion in the model. And this is actually a two-planet model. But it's kind of unsatisfactory, largely because the crossing of this caustic here is almost tangential. It's about 5 degrees from parallel. And that means that the source radius crossing time has to be very fast. This is a typical source radius crossing time of about 0.02 days, I think. But at this angle, then it means that the source radius has to be a few thousandths of a day, and that implies a very large Einstein radius, which seems unlikely to be correct. This data is not perfectly fit here. There's another high Ogle point here that some alternative models have as a beginning of a caustic crossing. So, and the problem with this event is because of this feature, it seems like we need to include the orbital motion as one of the parameters on our grid, and that slows things down quite a bit. And so this one would be good to devise, maybe a more efficient strategy for searching over parameter space. It's been quite a while since I worked on this, and so I'd like to see if people have other ideas on how to attack this. Yeah, so I think at this point, 1-star and 2-planet models or 2-star and 1-planet models are possible. It's true that part of the problem here is that the coverage isn't great. Some of it has pretty low signal to noise, and it's a number of short intervals from different observatories. All right.
So, Dave, can I make a comment?
Yeah.
In the previous event, I think it's useful for the audience to know, if they don't know already, that resonant caustics are the shape of the resonant caustic is extremely sensitive to the separation at a given mass ratio. And so generally orbital motion is easier to detect for resonant caustic events than planetary caustic events.
Well, they're also much larger, and
right.
So
that's
so you're more sensitive. I mean, you're sensitive to the planetary the resonant caustic for a longer time. Okay, so this one really doesn't have modeling difficulties, but it's only because we were lucky. So this is a planet in a binary system from Gould et al. 2014, I guess. And in the rising part of the light curve, we saw this dip, okay, in the light curve, and that's this crossing in between the two planetary caustics here, okay. And so this is rising to high magnification. We were expecting to see another signal of the planet. Instead, we saw a much larger signal due to a crossing of a stellar binary caustic here. So the issue here is it looks like we're pretty lucky to have passed through this caustic to let us know that there's a planetary signal there. If the trajectory would have come over here, and maybe with a bit of orbital motion or orbital motion in the other direction, or parallax in a slightly different direction, we could have pretty much the same signal here, but have missed this signal. And if that was the case, I don't know if we would have identified this as a planetary event so far. So this suggests that there may be a number of other planetary events that are sort of hiding in binary signals that haven't been carefully analyzed. Yeah. All right. So
I thought in that one, Dave, that if you excluded the planetary deviation, you still predicted the location of the planetary deviation.
Right. Yeah. So I should have made that point. Then they made this in the paper. So that basically, if you throw out the data around this dip, you still basically get the same model, and can show that the planet's there, but you don't have this smoking gun. And so in principle, we can detect this without that feature. But in practice, we haven't detected any such. And since it seems we're lucky to have seen this feature, then we would expect that there might be 10 other events that have planetary signals in things that we thought were binaries and haven't analyzed very carefully.
So, I mean, one question that comes up here is, in three-body lenses, if you have a third body that's much smaller, are there certain orientations where you perturb the central caustic of the binary more, or certain trajectories where that perturbation is more noticeable? Or is it the case that we're rescaling our errors for these binary lenses to sort of eliminate these deviations that are caused by circumbinary planets? Or
Well, I think it's unlikely that we're rescaling errors unless we're rescaling errors of very short duration data sets, just because, if we're rescaling the survey data errors, it's a very small fraction that would be on some deviation. I think it's likely that there probably is some dependence on the angle, because if you assume there's no dependence on the angle here, the odds of crossing that are less than 1%. So we'd expect 100 more events, which is probably not the case. So this is another event that's now published, and so this is Han et al. 2017, and so the new thing here is that we actually have MOA data on these, and MOA data cover what were supposed to be two different caustic crossings, and so this one occurs at the right time, and you see the MOA data sort of fits the caustic crossing here. It doesn't fit that well, but it's partly because it doesn't fit these other ones. And the main difference here is that there's MOA data here, and in the previous model, this Euclid point was on the end of the caustic crossing. And the MOA data don't quite fit that. And in fact, if you just look at the data here, it's not obvious that there's a caustic crossing anywhere. And so for this one, I mean, I had started modeling it thinking that there might be some other models, and
Can you show me the previous one? Did I include more data?
no.
Why not?
Well, I asked Ian to do some reductions, and he said he didn't think there was anything useful, and then I asked him to send it to me anyways, and I mean, I saw pretty clearly that there was we had coverage on this caustic crossing, and so yeah, I don't. Anyway, because we made a mistake, that's the reason. Yeah, so I think this one would be a good one to try methods to search for triple lens models, and also. I didn't see in your paper a discussion of binary source, binary lens models. I think, I mean, so, you've got one caustic entry here and another caustic entry there, okay? If you got two caustic entries in an event without an exit, then it has to be a triple, or it could be, caustic entries from different sources.
Okay, one comment for this event is that it's not just a matter of a triple lensing difficulty in triple lensing modeling. So just get rid of the the three-body third perturbation. Binary is okay. Superposition, this can apply. Superposition principle can be applied to this case. But so what you have to do is first find the binary solution. For this case, there can be many binary solutions. So because of that degeneracy, there can be also many different triple lensing solutions. So it's not just a matter of a triple lensing difficulty in triple lensing solution. This is a difficulty in binary lensing solutions.
Right. Well, I mean, my opinion is that I'm not totally convinced that by finding the binary lens solutions, by cutting out this feature and then perturbing from that, is actually going to guarantee to give you the right solution. I mean, after finding this, I also tried getting rid of this caustic and looking at, caustic entry here, caustic entry there. That didn't do quite as well as the way you did, which was the first thing I tried. But I mean, this model certainly does, this is the best I had, including the MOA data, and this certainly doesn't look right. I mean, this is not a great fit here. Clearly, there's a deviation here. This is not passing, this caustic crossing here. So I think this is unlikely to be the right model.
Gentlemen, in the interests of time, can I suggest we postpone this discussion until the hack session?
Okay. Yeah. So yeah. Well, I guess I discussed most of this already. Yeah, and so this is just summarizing the model weighting projects and then the triple lens projects. I did want to say that one thing that would really help with this is a faster way of solving the triple lens equation. And I know Radek has been working a bit on that. We heard from Valerio a bit on that as well. And so, I think it might be worthwhile to try and come up with faster calculation methods before working harder on the global search. Okay, I think that's all I wanted to say. Oh yeah. Oh, so the 9-year photometry data release. Yeah. So MOAA is committed to releasing this 9-year photometry data set. It's actually supposed to be part of JAXA's contribution to WFIRST. And so officially, we probably don't want to do the release before that agreement is signed. But what we'd be happy to have, if people want to work on the data, we're happy to work with them, and they can also help us to develop documentation so that the data are easy to use when you have the official release. So if you're interested in working on any of that data issue, let us know, and there's lots of work that can be done. Okay, thanks.
Okay, thank you, David. So, in the interest of time, I suggest we continue any further discussion and move on with the next talk, which will be Kaylin Henderson and Yossi Schwartzwald talking about the data that is publicly available.
All right. Good afternoon, everybody. Good to be here. Sorry I missed the first 2 days. Not contagious, I promise. I don't think it's related to microlensing, I think. So I'm going to talk about, primarily focus on the NASA Exoplanet Archive, which is where I work. I'm a research scientist at IPAC at Caltech, working at NextSci on the archive. I'm giving this talk on behalf of the whole team. I've listed the names. Rachel Akeson is in white. She is also here. So feel free to ask her the hard questions, me the easy questions. And then at the end, Yossi gave me some slides. I'll actually give that portion of the talk as well to discuss KMT-net data policies, about which we heard a little bit earlier in the talk. And before I even jump in, I just want to say, really excited. I feel like even 1 year ago, this kind of a talk and then having a whole afternoon of public modeling code talks and discussing a data challenge and having a hack session, I don't think the field was really at that point. And yet here we are, just 1 year later, and we're discussing a lot of these public resources. So I think it's maybe we've already had a watershed moment. So what I'm actually going to open with is, since I didn't get to give my research talk, unfortunately, I'm still going to show the cool animation that I was working on. So this is for the event OGLE 2015 Bulge 966. This was observed in the second year of the Spitzer campaign. And as part of the KEC, Key Strategic Mission Support, the KSMS project, we obtained JHK photometry. Not going to give away the punchline, just to say that it's underway. And I'm showing this here as a nice segue to what this talk is actually about. What I want to say is that everything that went into that animation that was showing the light curve was all publicly available. So all of the data sets that I was using, ground and space-based, downloaded the time series from the NASA Exoplanet Archive and made available by Rachel Street, who's the first author of the discovery paper. To do the actual event and model analysis, we was using MuLens model, one of the 3 public codes you'll hear about this afternoon, and then was using Python. So unlike IDL, there's no license fees. And I should also say that I was also using quasi-public knowledge from Radek Pileski, who's been a lot of help in using MuLens model. And he's shown here, wondering why I'm still using the same joke for his name as I did 2 years ago. All right, NASA Exoplanet Archive. So this is a screenshot of the homepage. Hopefully some to all of you are familiar with this. If so, you can snooze for a couple minutes. If not, I'm going to walk you through some of the basic functionality and different tables that we have. I'm going to begin by describing our 3 main tables, kind of the bread and butter, or gluten-free bread, and dairy-free butter, as you will, of the services that we offer, and where to find them, how to use them, what you can do with them. Oh yeah, I forgot. So I was a little sick earlier, and so idle hands are the devil's work. So I'm using a picture of me blowing a horn, out in the steppes of Utah to show just how excited I am about all the things that I'm telling you. So I'm pretty excited. This is 2 horns, pretty excited. So confirmed planets, this is our main table. You can access it at least 2 different places off of our homepage. And what this shows is a default sorting of what do we know for an identified default parameter set for every confirmed exoplanet in the refereed literature. There's a lot of features of this table. So you can do column sorting on numeric and alphanumeric values. You can filter, and you can do multi-column filtering as well. So you could select, say, microlensing planets. You can also do column pane selection. So there's a lot more columns and parameter values that we're carrying that are not displayed in the default selection. And you can mix and match as you choose. And I didn't even know about this until 1 or 2 years ago. So I'm betting that a lot of people in this room didn't know this. There are actually features that you can create an account, log in, and save user preferences. So if you want some sort of different default display or sorting or ordering, you can set all of that up so that you have your own customized view of the confirmed planets table when you log in. It's very, very helpful. One of my favorite things is that this and all of the tables I'm going to be discussing are also queryable via API. I'm very excited about this. So is one of our users who tweeted at the NASA Exoplanet Archive once he learned that we actually had API queryable functionality. And the Homer, for those of you who don't know, Homer drooling, this is a good thing. This means that he's very excited about having API functionality. #geek, #nerd. Very cool. So that's a confirmed planet table. In 2018, we also rolled out a new table that mirrors a lot of the data that we have in the confirmed planet table. This is called the composite planet data table. It's new, giving it 1 horn. Here's the composite planet data table. Very similar interface, all of the same functionality is confirmed. The difference is, whereas in the confirmed planet table, every single row corresponds to 1 parameter solution for a confirmed exoplanet pulled from a single literature source. Here, what we've done is, in order to just, sometimes you want to do a quick look of all of the parameters that you might know about a given exoplanet, even if they're coming from different data sources. And so this aggregates all of that. We try to give a disclaimer that people heed that indicates that these are not necessarily self-consistent parameter solutions, especially if stellar and or planetary parameters are pulled from different sources. So just be aware of that if you're interacting with the composite, but it is a much more complete and comprehensive table because of that. We have also implemented parameter calculations, things like planet mass and radius. We use the Chen and Kipping 2017 relation with all of the caveats that come in using that, and planetary density and a couple of other parameters as well, stellar luminosity. So that's that. And then our third table, this is extended planet data. It's only linked to 1 place on the front page, 1 horn. And here is where, rather than showing only a single default parameter set for every confirmed exoplanet, and rather than aggregating data from different literature sources, we are storing, allowing the user to access any parameter set that exists for any confirmed planet. So this means that the number of records is much larger than it is for any of the other 2 planets, which is exactly the number, any of the other 2 tables, for which the number is exactly equal to the number of confirmed planets, a little bit under 4,000. And so you access it through a search interface rather than an interactive table. Here I put in HD 39091. I don't know if anybody knows that phone number off the top of their head. Unofficially TESS1, also PyMense, B and C. And so if you query an individual object here, you actually get every row corresponds to a different but self-contained parameter set for that object. So here you can see in the PyMense system, for example, the B planet was already discovered by radio velocity many years ago, and then it was the C planet that TESS picked up late last year. So now just some other things that I'm not going to go into too much detail about, just to highlight. You can get some quick look pre-can statistics available from the very top right. You can do an inventory search. Any object that you're interested in will take you to our overview pages. I'm not going to show you those, but hopefully you're familiar with those. There are also project deliverables that we store, light curves, threshold crossing events, a lot of information about the events and the candidates detected by the Kepler primary mission. There have been other ground-based photometry and transit services that have agreed to allow us to host their data here. Kelt and SuperWasp are two of the main ones. There are other ways that users can contribute data. So this includes a link to our sibling site, the ExoFOP, the Exoplanet Follow-Up Observing Program. This is for helping organizing coordinated follow-up and simultaneous observing campaigns on contributed data, things such as time series for microlensing events and others. There are also a lot of tools people can interact with in browser. Periodogram. If you're planning an observing proposal or looking for a target on a given night of observing, you can use our transit service. ExoFast if you want to do simultaneous transit and RV fitting. There are also pre-generated plots. You can use visualizations that we already create and that are up to date with all of the confirmed exoplanets. There's documentation for everything. Anyway, getting very excited. There's a lot here. 10 horns, 10 out of 10 would horn again. It's very, very exciting. Now I'm going to transition to talking about the actual microlensing specific stuff. So here's a specialty table that has existed for a couple of years, but we've really revamped it in the past 12 to 18 months. Accessible here. I only put one horn because we all know about it. We're all excited. I don't need to jazz up enthusiasm about microlensing. Similar table interfaces previously with the confirmed, the composite, and those two tables. Except whereas those tables, since the vast majority of exoplanets have been discovered by transit and also RV, and there's a lot of natural synergy in the observability of those targets using those two different techniques, that means that those tables are essentially dominated by observables, fit parameters, and physical properties that you get out with transit and radial velocity. The microlensing table is kind of our niche corner where we have all of the microlensing specific parameters, observables, and physical properties. Here have included degenerate models, anything that's statistically indistinguishable or that's presented in a paper where there is no clear or preferred solution. We have ingested all of those data. And this is work I want to highlight that I did with an undergraduate student, Eileen Tagnon, from San Diego Mesa College. She is currently applying for RUs and undergraduate transfer programs. And so I just want to advertise for her. She's amazing. She's smart. If you see her name on an application, much like a microlensing event, her star is getting brighter. So I encourage you to keep a lookout for that. It's the first animation I've ever used in the talk. That went great. We also have all of the time series and public data for the UCURT microlensing survey. This is available. It's under our transit survey box, but it's there. Here's a picture of Yossi Schwarzwald, the PI, who's realizing in this moment that the schnozberries taste like schnozberries. And on the top, I've showed the different observing footprints for the different years of the UCURT survey. So it started in 2015 in support of the second year of the Spitzer campaign, about 3 square degrees in the northern bulge fields. Then in 2016, area doubled in order to cover the K2 Campaign 9 super stamp. Both of those campaigns were in H-band exclusively. Then in 2017, we began the first year of a dedicated survey in support of WFIRST to try to measure the near IR microlensing event rate across the actual target field region that WFIRST is planned to survey. There's 2 outlines in the plot on the right. Those are showing sets, both of northern, so positive galactic latitude, and southern that were being considered. After a preliminary analysis of the 2017 data, realized that the extinction, or that the event rate was not so much higher that it would probably warrant continuing to consider observing at positive galactic latitudes. So starting in 2018, we focused exclusively on the south. You can see the different cadences and all of the numbers there. This is to say that there's a lot of data and a lot of public data. So if people are looking, Mo is coming out soon. I'll talk a little bit about KMT at the end of the talk. But everything that we've collected for UCURT is available now on the Exoplanet Archive. And you can go through there and apply your favorite machine learning event identification and classification algorithms. The search interface is similar to the extended planet data table. There are millions and millions of records. And it leads you, when you enter a search with certain criteria, to the same sort of interactive table interface. What I've done here is searched for all events in 2018 with an OGLE and MOA, oops, skipped ahead, with an OGLE and MOA event match. And so I just want to use that to highlight that both of the OGLE and MOA collaborations have agreed that we can essentially publicize that information. You can also link to the corresponding OGLE and MOA event pages from there. And I want to highlight the work that Savannah Jacqueline, who's shown here, happy that my talk is almost over, which means my jokes are almost over, who has a poster outside talking about some of the machine learning that the UCURT microlensing team ourselves that we've actually started to apply to do event identification and classification. Go check out her poster. It's great. So now here's some slides that Yossi gave me to talk about KMT. Since they're Yossi's, the horn density is not going to be quite as high. For that, I apologize. So KMT, as everybody in this room is hopefully aware now, I think Andy gave an overview talk on Monday. Three-site telescope network in Australia, Chile, and South Africa. Here's some nice pictures. I think these are slides maybe from a talk by Chung-Uk Lee, so thank you to him as well. So 1.6 meter aperture, 4 square degree field of view on 0.4 arcsecond plate scale. These are the most recent iterations of the KMT bulge fields. So you can see covering cadences of about a half hour to once every 5 hours, focusing on the inner part of the bulge, kind of the standard region for optical ground-based surveys. And KMT also has a public data policy. So showing screenshots here, the URL is at the top, but come and ask us or any member of the KMT team if you want. Events that have been identified and thus published by the KMT collaboration on any of these event tables are public, but of course, talking to them to include them as co-authors on papers is always a nice thing to do. Down here at the bottom, you can see that they have 2015, 2016, and they split the K2 Campaign 9 and non-K2 Campaign 9 events differently, and then there is 2017 data as well. Here's an example of one of the year's tables. So this is somewhat analogous to the OGLE EWS and the MOA TAS. They have a bunch of kind of standard plots, finding charts, initial parameter fits, coordinates. They include a PISIS light curve, color-coded by the different observatories with links to the actual photometry files on the right. And then at the bottom of each event-specific page, you also see the DIA extracted photometry results as well, again with links to all of the DIA data files. That's the end of my talk. I'll take questions.
Any questions for Yossi? Oh, yeah.
It hurts.
Question. I noticed that sometimes the microlensing table and the general exoplanet table are not really exactly the same. Do you have a reason why? Like some examples, some events are missing. Or I noticed that between the microlensing table planets and the general planets on NASA exoplanet, archive. I realize that sometimes they are not really. There are some events missing, for example. Do you have?
Yeah, I guess it's so the microlensing table itself. It's only about 70% complete. So maybe it's the 30% of events. We only had Nylene, unfortunately, for 10 weeks, which wasn't quite enough time. If there are other events that we're actually seeing parameter mismatches between what's represented in the tables, yeah, definitely let me know. Can identify those.
Jennifer.
Data holdings for microlensing planets?
Yeah, I don't actually remember the exact numbers off the top of my head. I know Rachel Akeson had sent out a call maybe a couple of years ago to ask for any photometry that first authors of papers for published planets would be interested in donating to the archive. The one in the gift that I was showing at the beginning, Rachel Street had donated those, or had allowed us to host those publicly. I don't actually have a sense for what fraction of events we have all of the photometry. Do you know?
At that point, we became very complete, probably 80 or 85%, but we've probably been a little lax following up in Confirmed Planet since then. So if you have a recent, in the last 2 years, if you have photometry that you'd like to send us, please do. We'd love to host it.
Yeah, I think Radek has been the most proactive. Thank you for that. in sending us photometry. But yeah, especially the past 2 years were more incomplete than prior.
Any further questions? If not, then we'll move on. Thank you again, Kaylin. So the next section of talks gives an introduction to the publicly available software. We'll start with Etienne Bachelet talking about Pylema.
Yeah, hope you hear me. Yeah, great. Okay, so I'm gonna start with some slide, and then because it's a hack session, I thought showing some code was a good idea. So let's start with the slides. I will give a quick overview of the Pylema current status, and then I will explain how you can feed a PSPL binary model and how to simulate with Pylema. And all the materials I will present today are available on this GitHub repo that I just created, so it might have some bugs still, but we can discuss it later. Okay, so you see this plot this morning, so I'm not sure I'm gonna spend too much time on it, but yeah, this is the current status that we have. Okay, so to fit PSPL event, you have some basic step to do. So then you create what we call an event object. So this is a general object that give basically a radar in the sky. And then on this object, you can feed observation to him. So this is done with a telescope class object that you happen to list to this event object. And third, you need to create a model object based on this event. Like if you want to feed parallax, etc., you need to inject that. And on the first case I will present, it will be a PSPL. And let's say you want to feed after that a USBL model, so a binary model to this. You just create a new model object, which it's binary, and you inject it in your event again, basically. And if you want to simulate an event, it's kind of similar. You create an event again, you choose an error deck, you simulate some telescope observations, so there is a module in Pylema who does that for you. Then you simulate a model object of what kind of light curve you want to see. You have to give the model parameters of obviously to relative to the model, and then the light curve are generated automatically. Okay, so yeah, okay. So that's the end of my slide. Let's try to make it work now. So what it done in an IPython notebook, it's like this. So I have to say this IPython notebook I created specially for this event, but it's mainly based on the one on the repo. So for those who are familiar, you will not be too much. Gee, that's nice. It's not. Can I increase the size? Yeah? Okay. So, as every code in Python, you first import your library, so NumPy, obviously. Then you import the event class, the telescope class, the model class as a start here. And as I say in my slide, you create an event object. And so I keep this event secret so far. So a friend of mine gave me some data. So I don't know what is it. So you can give it whatever name you want with some, don't put too much crazy character on this because it's going to crash. And then my friend also gave me some data. So I have this data here. Of course, if you download, you can change the directory if you want. Okay, so this line, what it does, basically, find in this directory every file there is there. So this is a light curve, basically, so time magnitude error mag. And here I iterate and I open this light curve and each time I create a new telescope for each observation. And to see what it gives, we're gonna plot the light curve first because my friend could have made a joke about it. And in principle, it should crash. Yes, okay, that's good. And no, it works, so that's even better. So you can zoom a bit in Jupyter Notebook for those who are familiar with it. It's a bit painful, so let's have a look if our friend was nice or not. Here you go. All right, so to me it could be a microlensing event, right? So we're gonna try to fit that. So as I said before, the last step to do is to create an object model. So here you create a model. Then we're gonna start with PSPL first, and we're gonna fit with gradient, so 11-bit markup. So PyLima, there is a routine for PSPL. We try to find some guess, because for a gradient method, you need guess on your parameters, right? So it does that for you, and in principle, it should give you a fit. Right, here you go. So this is the best fit that we found. It's not too bad. But if you zoom a bit here, you see that there is a little blip. So okay, it's a bit more complicated than a binary, maybe, than a PSPL, sorry. Here you have the parameter of the best fit. But someone can say, okay, I don't really like your routine for finding guess with PyLima. So what about we try a more general search? So here it's differential evolution, basically. And we just restart a fit, and we plot the output. So you can see here, I'm going to plot the output of the second fit. So each time you fit on the same event, the number of fit you do is listed in a list. So it's stored in memory, basically. So let's have a look if the guess was good or not. All right, so differential evolution is a global search, so it takes more time, let's say. All right. Oops, forget to do something before that. Need to kill this IPython plots. Here it is. So this is a D fit now, and as you can see, it's more or less the same thing. So it sounds like our guess was not too bad at the first place. And no, not this one, sorry. Where is it?
So this is still trying to fit it with point lens.
Yeah, it's still point lens because here we inject the same model one, right? So this is a D fit basically, and this is according light curve and etc. So let's try to zoom again on this. All right, so no magic. We still don't fit this anomaly here. All right, so what about we try something else? So let's go for binary fit now. But as you heard since maybe 2 days, binary fit is much more complicated than point source point lens. And still, for this presentation, I wanted to keep it quick. I will use gradient as well. But hopefully, my friend give me good guess on it. So I'm going to use that. If you want to know how to find this kind of guess, we can discuss later. I can give you his email address. And so, oh, all right, that's okay. My battery is dead anyway. So, no plot anymore. No, I'm on battery. Oh. Oh no, I'm not. All right. Okay. Well, basically, the fit was working. Um, and but that gives you the flavor on how it works. So basically, in 4 or 5 lines of code, you can ingest the lie curve and fit your event in, I hope, a kind of easy way to understand for those who are familiar with Python. And the last slide was about simulation, which is actually kind of similar. So you create an event, you create a telescope object that you give a starting date, an end date, sampling. Do you want uniform sampling or not? Or because we implement some of the very nice AstroPy function, like if you give, let's say, an ogle location and some elevation limit, it can mimic real observation, like your telescope can go below that. So that changes the sampling of your light curve. Yeah, that was it. Okay, let's.
The only thing that you could do there that you needed to change was change the model class, right? So instead of doing point source point lens, you did.
Yeah, USBL. I'm not sure if you saw that or if I explained it enough. Oh, he's alive. Yeah, seems kind of alive. So that's okay. All right, so I can still have 2 minutes. I can quickly show the simulating. So to reply to a question, Yanni, we just changed the model here, and you see it's model 2 that we fit here, right? Oh, yeah, you're right. Probably people are interested by that. Let's see. Well, looks okay, right? More. That's convinced me enough. All right, so let's kill it now. This stuff, right? And give me a minute, Yanni. Okay, so now we can simulate quickly. So here I close all the figure. I import the simulation thing. I simulate an event, which actually the name is wrong, but never mind. So the telescope I'm simulating here will be called survey, and between this time and this time with a 48-hour sampling, so 1 point every 2 days, but it doesn't really matter because, no, sorry, forget about that. Then you inject it in your event. Then you say what kind of model I want. Let's keep things simple. So I use a PSPL again, no parallax, no XRF, no orbital motion, no source spots, whatever. And then I want these parameters, right? Here, PyLima can simulate the flux based on some magnitude distribution for the blend and the source flux. So you add that to your parameter, and you transform it in a PyLima format, let's say, and then you simulate the light curve, and finally we plot it. And in principle, there you go. You've got your very nice PSPL event, so, and you can play with it. Thanks.
Just in time. So we have time for a couple of quick questions, or we can. Oh, Yanni, yes, go ahead.
Is there a way to kind of plot the differential evolution surface?
Yeah, because we have a list. We keep track of every point during the exploration.
So you can plot that easily?
Yeah. Okay. Actually, I can show you after. I have some quick code to do the global search for this event in 20 minutes. So.
Okay, thanks.
How is the documentation of the various different functions that PyLima provides? Is that easily accessible?
So in principle, there should be an automatic documentation each time I update the code on GitHub. So you can see, oh yeah, one thing which is important, the unit tests are crashing right now, but it's not too bad because it's only crashing for Python 2. So that means we switch to Python 3 mainly support. So I encourage every people to move to Python 3 because a lot of tools that you use will not be supported in Python 2 anymore. So that's fine. And the documentation is here on the website. And well, we give you some advice, and if you want to have to some model documentation, you can go there. This one is quite short. Let's take this one. I try to explain everything, and this is using the marvelous things who do that everything for you. So this is the transparent part of the black box, actually. Yeah.
Okay, thank you very much, Etienne. Okay, so the next up is to tell us about their most recent code. This is Radek Polski, responsible for the Microlens model code.
Yes, I'll be talking about Microlens model code. So if you want to see it, just go to this GitHub website. The code at the beginning was started by Jennifer E. and me. Now it's mostly me working on it, but also Jennifer is consulting me, and any input is welcomed. So first, a few things about the code. We're trying to write a code that is transparent to the user. And we have very different philosophy than in Pylima. So there's no built-in fitting routine in this code. It doesn't fit any event at all. I tell you right away, and that's how it is. Though, we give tools to fit the events. So most importantly, there's chi-square calculation tool that calculates chi-square for given data sets and given model. And these models can be from a wide range of possibilities. And we also provide examples. So if you just want to, if you think you have something simple and you just need short answer, you can just use one of our examples and it will give you some answer. There are many degeneracies in Microlensing model fitting, so that's one of the reasons why we're not giving the fitter. Fitting is on you. Yes. Code is object-oriented. It's written in Python 3. Should work in Python 2 as well. I've heard many things work. I don't test it. To be honest, I work only in Python 3 right now. There's documentation. There's full description of every single function, both input and output. There's software paper that describes the version of the code, which was like half a year ago. Oops, sorry, 2019, not 2009. It's in astronomy and computing. If you're not familiar with problems that we deal in Microlensing model fitting, I suggest you read sections 1 and 2 of the paper. They, I think, really well explain what problems can appear in fitting Microlensing models and using very automated codes. We work on the code. It's constantly developed. If you need something and it's relatively simple, that's added very fast. If you need fully automated triple lens calculations, yeah, I know it would be good to have one, but it's not there yet. There's a wide range of models possible. We have satellite, annual, microlensing parallax. We have binary lenses, binary sources. You can combine binary lens, binary source, and add microlensing parallax. There should be no problem with that. There are also different parameterizations. There are a few different plotting tools. So there's quite a wide range of possibilities. Finite source binary lens calculations are like the hardest you can do right now when it comes to calculating magnification. So for that, we're providing both simple things like hexadecouple approximation, but for full modeling, you need either VBBL by Valerio Bozza, which is most widely used. So thank you, Valerio, for providing this publicly. So it's also wrapped. We have a wrapper around Valerio's C++ code, and there's also adaptive contouring by Martin Dominic. That code was released a few years earlier, but it's also available in Microlens model. There's no problem in using either of them. And if you just don't want to think which method of calculating magnification you should be using, you can use VBBL for whole light curve. There's no problem with that. So you can use it. It may be slow, depending on your event. So maybe it's not slow, but there are faster options if you know when to use which codes. But you can use VBBL for whole light curve, should be no problem. So now, 2 examples. I'll try to show how fit, first of all, point source, point lens model, which is very simple fit. And to make it really simple, I'm just fitting using SciPy optimize.minimize, which is, I don't know even what. It uses some method to give you some values of parameters that well fit the model. So here's the code. It's just 2 slides, so I hope you will survive. So first we do a bunch of imports. Then we slightly change how the chi-square function is defined in Mulens model. So I'll get back to this in a second. Then we need some data. So this specifies the path to a file. The file is for OB0892, and it only ogle4 data, so there is just point source, point length event, and here Mulens model gets in. So to have a Mulens data object, you just construct it and you provide the file name, and that's it. There are parameters of the model, so it will be T0, U0, and TE. Some initial guesses, so if you look at the light curve of that event, you can easily guess some parameters. Then we start with the model object. So the model object is something that combines the information you probably really want to have in the paper. So these are like the parameters of the model. So model object and event object in Mulens model are different than in Pylema. So yeah, we have same names for different things. So when you construct model, you just provide names of parameters and some values. In this case, these are our initial guesses. So you provide a dictionary that combines those two. And then we construct event. And event is a combination of data, which we constructed here, and the model, which we constructed a line before. And that's basically everything you need to fit. Just going back to this function, this function takes a list or a NumPy array of parameters, takes our event object, that one, that will be the same one as here, and then takes the parameters that are changed. And then for every pair of value and parameter name, it sets the attribute of the event to this value from theta, from here. And then it returns chi-square. Hope it's easy until now. And then the fitting itself, here I did it with this SciPy routine. So I provide the name of my function, the initial guess, these additional arguments that are passed to the minimized function every time it's run, and I specify the name of the method, which I don't know even what it means. And then I just print the results. Yes, so these are the results that are best fitting chi-square, also the chi-square itself. And here I do the plot. It takes few lines. The really important ones are plot data. It just plots data. Plot model. From this time to this time, it will plot the model. Then in a second subplot, we'll have plot residuals. So it will plot residuals. So when you run it, you get such a light curve, and the results it produces T0, U0, TE, and the chi-square. And that's it. That's simple fitting of point source, point length model. So going to more advanced example, I will use Dan's MCMC hammer and try to fit finite source binary length model. And in Mulens model, there is no fitting routine, so I'll show how I would fit this event. It doesn't mean that that's the best option, that's the fastest option. That's just an example to show you how it can work. So that's how the event looks like. So it's the same as Etienne shown for Pylema. And you can see T0 is here, yes, so you can read the value. The event is short, probably a timescale of 10 days, and there's some anomaly over here. So what I did for that, I wrote a short script that is available on GitHub, and I can discuss any part, but all the parameters in this case are passed via Python config files. So first, that's just a text file that you produce. First, in my config file, I said what are the photometry files. We're using magnitude or fluxes, so I specified that in each case, these files are in magnitude. If you have data in fluxes, just write flux there. For some model parameters are methods, so we'll be using VBBL during the time of the anomaly, so it's just these 3 days on the anomaly and close to it. And the default method for calculating magnification will be point source point length, because that's enough, that's very stable and very fast. So that will speed up calculations slightly. We'll print all the models that are calculated. For plotting, we'll use just this time range. And for MCMC hammer, we need some settings, so number of walkers, number of steps for each walker, and the burn-in, which we'll use. So that's this. Second part of this config file is starting parameters. So we have T0, U0, all these other parameters, and we're taking them from this distribution. This is like Gaussian with this mean and this sigma. We have log uniform for Q, which from 10 to -5 to up to 10 to -3. So really wide range of especially Q, S, and alpha. We have no knowledge what's alpha. And then we also have to specify some prior so that minimum and maximum values that can go. So like alpha should be between 0 and 360. TE should be positive value, so that's also good to give those. So then when you run it, you just run Python. Then you provide the file, which probably I would not explain fully, and then this config file. It starts printing some models, so it gives first chi-square, and then all the parameter values. And these are, it produces lots of them. At some point, it arrives at chi-square of around 1,000, which means for this event, it shows that it fitted the main event, but not the anomaly. And then at some point, you see there's very low value, chi-square of just 700. So I stopped the calculations at that point, and I changed the config file. I produced the second config file where I've set the T0, U0, and those values close to the values in this very good model. And I did a few more changes in the code, so changed number of walkers and so on. These are like minor changes in this config file. I ran the second config file, and after 10, 20 minutes on my laptop, I don't remember, I got this full table with all the parameters fitted. Most importantly, we see Q is very small. That's the best fitting model. Corresponding chi-square is just 560, so it's much lower than these previous models. And it also produces a light curve plot. And that's it. And I have 2 seconds. Thank you very much. Ask me questions about any specific part. So I haven't shown the code for all of those calculations, but I have many slides to show it if you want. If you have specific questions, then that's the time to ask.
Beautifully timed talk. Well done. Any questions for Radek? Yanni?
So it seems to me that you are looking for you find a local solution, right, in the global. So how do you explore the entire parameter space and make sure that you do not miss any solution? Because that you don't really need the MC. I mean, you could do it with a simplex method, right, to converge to that solution, which is a lot faster than just using MC, right?
So I ran MCMC hammer twice. First, I ran it with this setting. And the starting parameters were like alpha is uniformly choosing from 0 to 360. So I'm trying to explore full parameter space, I would say, yes. And like log Q, these 2 decks, you can make it wider, and then of course you will find the first good model later. But of course, I'm not sure if I have explored everything. To be honest, I did a check for this event, and I looked for a smaller than 1 solution, which has significantly higher chi-square. But there is such a solution as well.
You have to run it separately for all the possibilities.
In this case, you would either run it separately or set this uniform from like 0.1 to 2, and then analyze the output that EMC returns, and you have to do it on your own.
Excuse me, Valerio.
So, just a comment about the window in which you use the BBBL. Well, outside this window, you use PSPL. Actually, this is not really appropriate because, in principle, VBBL is as a coordinate system centered on the center of mass of the system. So when you switch to PSPL, actually you are suddenly moving your source, your star at the center of mass. So it's not really appropriate. In this case, the planet is really, really small, so it works. But in general, this is not appropriate. What I recommend is to use VBBL everywhere because you don't know in advance if your anomaly is confined in a short window or you have a long-term perturbation. And so by default, VBBL will take care of everything. And in any case, in the latest version, it basically starts with the point source of binary lensing, and so it only uses the finite source, the full finite source calculation, which is much heavier, only when the quadrupole term is high. So in general, well, this is just for
yes.
the
Yes, and as I said, it's not general fitting code. It's just how I approach this particular. And to be honest, I've read the paper about this particular event, so I knew before. Yes, I was biased. Yes, so you can, as I said, you can use VBBL all the time, or adaptive compute contouring by Martin, and there's no problem with that.
But this was an excellent introduction and demonstration of a very powerful package. So thank you, Radek. Our next presentation will be the Mulan code, which is developed by Clément Ronc and his team. Sorry.
Hi.
Over to you, Clément.
Thank you. Can you hear me? Yeah. Oops. Okay. Yeah, so thank you. So I'm very happy to present, actually it's the first time I present this modeling called Mulan, mainly developed by Arnaud Cassan and I. So what I will do is that I will show you, it's really like a brief introduction, and I will show you how to use it and how to modify it, how to use it as an experimental tool. So Mulan, what does it mean? It's actually does not refer to the movie. It means like microlensing analysis software. So this is a Python 2.7 based code, much less object oriented than the PyLima and Mulan's model. And yeah, so for all the example I will show you, please, like, if you want to reproduce, you have trouble to reproduce this, come and chat. Stella, if you can identify yourself also, Esther have already, and Yanis have already used it. So if you want to have some advice, please come. So what is Mulan? Mulan is a tool that allows the computation of the magnification, mostly wrapped as all the other package of the routine written by Valerio Bozza in C++. So it includes, of course, single lens, binary lens model, finite source effect for all the model, limb darkening, parallax effects, lens orbital motion. But it's not only a way to use Valerio's method. There are also other methods like hexadecapole approximations, the last development published by Arnaud Cassan, and any other method you would like to experiment can be added. It's a fitting tool. It's actually built in. Mostly, so it allows grid search. It allows also to use affine invariant method based on Dan package, EMCEE. It's a plotting tool to look at the dataset, and I will show you immediately after. And yeah, and there are some tools to get some ideas of what about the statistics of the result you get. So the general requirements, so the first step is to create a directory that include a number of subdirectories. So the archives will be a directory where the code will keep track of each model you try. The chains are mostly used by Mulan, but you don't really need to go inside. The data are where you put every data set you may have. You have to put them in the data subfolder. The output will give you some every information you do need or you do want when you want to publish a paper to do your own plots. And yeah, the plots, like you understand. Of course, everything is you can choose other names and other structure. And then there are the configuration files that are very important because they drive how the code behaves. And there are three main parameters: setup, observatories, and advanced setup. So let's start with the observatories.ini file. This file includes actually all the information you need to know about the observatories. So here is the name of the data set you will want to consider. Here is the name of the files. And then after you have a number of information, the full name, the color you want for the plot, the passband, is it magnitude of flux, what location. So this keyword refers to some ephemerides. And yeah, so this is mostly. So basically, once you have this file, you use, you can use always the same. So now, how does it look like on actual events? So I will take the same example as before. The first thing you want to do is to look to your data. And so we have seen that because you have data sets from very different observatories, they are not aligned. So sometimes it's kind of difficult to look what information is in your data. So let's go in the setup.ini files. And the setup.ini file includes several sections: the event description, some keyword to control. So here I want to plot the data. Then I say in this configuration file which data set I want to use. This is the rescaling factor let's forget for now. And this is the time interval in which I want to take into account the data. And yeah, and here in the plotting section, there is, so don't be afraid by the keywords. You will understand actually where does the keyword come from, and you will create your own keyword soon. And so in the plotting section, you choose to align data, and you choose a time interval. And so if you do so I would like actually to show you this, to show you a little bit how do we interact with Mulan. So I am in the right directory. If I do ls, yeah, I have the structure I described. And so if I do python mulan.py, so yeah, I have a lot of things running on my computer. So here is the setup.ini files. We recognize your data line that I just described. So there is a lot of things because I did fit the binary lens. So there is a bunch of information in the terminal, like a summary of the details about the event, and he finished. So if I go in the, if I go on the plot subdirectory, okay, I have a HTML file that has been created and that plotted the data. So I can have a look to this data. So this was not a fit. It's a kind of non-model dependent alignment to have a quick look to the data. So this, we recognize the anomaly. This is maybe the first thing. Okay, where is my, oh no. Yeah, I was sure that this would happen to me. Okay, sorry. Well, so now you know everything on my life. Yeah, let's come back to the events. Maybe, okay. So second step, I want to fit a point source, point length. So the difference here is that we will need to include a modeling section with some minimization methods. And so the PSPL rely on 3 different parameters, T0, U0, TE. And so the way Muline is working, so again, this, maybe I will show a little bit here. So the way it is working is, so the name of the parameters, it depends on the routine you are using. Here is PSPL. So what does it mean? It means it's difficult to explain to everybody without at the same time. So you have the line models Earth. So this is because I didn't include a different position for each telescope. I just said this is the center of the Earth. And, but I could have one line per telescope. And I say that in this time interval, I want to use PSPL. Okay, and I include the 3 required parameters. I say that I want to fit them. And the algorithm we use the value that is taken, that is given at the end, and will initialize the EMCEE. So initialize numerous chains. Here I chose 12, as you see, in an interval that correspond to the median. Thank you. This value minus this value plus this. So you can also change that. So let's do it. It was super well organized. I swear this before. Yeah, this is the PSPL. So if I fit using the affine invariant Markov chain. Oh, so it asked me, oh, be careful, you already fit. So I say, yeah, do it again. So here is again the same parameter file. So you recognize what we did before, and hopefully will be very fast. I chose a length of 100. Okay, so this is a summary of the fit. And if I refresh, this is what we get. So is it a PSPL? Yeah, it looks like it is a PSPL. And again, so it does not fit very well. It does not fit at all the anomaly. So this is a little bit to give you a flavor of how do we interact. So I come back here. Okay. So you can do exactly the same thing, but this time you can include binary model. So here I use the Valerio's Bozza contouring method with a uniform source. I add the required parameters and I fit it the same way. And I will comment a little bit on it. So what you can see in front of the parameter S and Q, there is the GRI. That means that I want to do a grid search on S, on Q, on alpha, so the angle of the trajectory. And for each node of the grid, I do a Markov chain Monte Carlo. And so if I do that, so this is like a rough, so it takes time. It takes more than an hour. So if I do that, you see that I start to fit the anomaly. If you compare like the parameters the model found is pretty close to the right model, and we would need actually to refine this model in the real life. Okay, I switch that. And I just want to tell you to conclude how to modify the code. If, let's say, I want to, for example, yeah, if I want to add a new way to, for example, to compute the magnification, let's say a triple lens algorithm, then if you go in Mulan, you have a model directory, and you can create basically in this. So the way Mulan is working is it is working with wrap functions. So as soon as you know what is the wrap function, you can write everything you want. As soon as your routing includes some wrapping function for the magnifcalc, for example, you can use your routine that you call how you want, and you can use it to compute the magnification and to model any light curve. All right, so this is, I stop here. Please, if you want to play a little bit, to experiment, come to see me. There is, this is the GitHub repository, some documentation, and that must be improved. Oh, yeah, and the improvements like we are currently doing, so are very much related to the different MCMC methods, and especially we are like testing library, the use of pre-computed light curves to speed up the process of the first search. Yeah, I'm very sorry. I'm way too long. Okay, I stop here.
Thank you, Clément. I hope if you have questions, you'll catch up with Clément later. In the interest of time, we have one extra talk that was not originally on the schedule. So I'm going to ask to move along and invite Valerio to come and tell us more about his system real-time model.
Just 1 second while we pull up that presentation.
Yeah. Well, sooner or later it will arrive. Yes. Well, it was just an extra presentation because, I was confused about this scheduling of the hack session. Anyway, just to
Did you put that in the Dropbox?
Sorry?
Did you put that?
Yeah, I put it on Dropbox.
Day 3, or under hacks?
Hack session.
Hack session. Stand by.
So, just a short summary of what the RT model does. I want to emphasize that RT model is not a public code, so it's different from the other. So it's very. I really appreciate the efforts of the other people working on on public codes. So I actually concentrated on the VBBL as a public code, and so I'm happy it is widely used. But in this case, what I want to present is some algorithms that can be useful even to trigger new ideas and probably be incorporated in some of these codes. And in particular, I would like to focus on some new ideas that came along with this data challenge. So in particular, RT model is a platform that is designed for real-time microlensing modeling. It is active since 2011. It allows data from Artemis automatically, and it makes a complete modeling without human intervention in less than 2 hours, or typically 1 hour, depending on the number of data points on a single workstation. Calculations are done using VB binary lensing as all other people, of course, and all the results are posted on a web page. And so this is just a summary of the events that have been modeled by RT model along these years. Okay, so the structure of this of my modeling code is entirely written in C++. There is a main module that calls several submodules interacting via ASCII files. I don't want to spend much time about the list of all modules. I just emphasize that in every modeling phase, you first you have a data preparation and preprocessing phase, and then you have a setting of initial conditions, and then you have fitting with all possible models that you can expect in a microlensing event. And then and finally you have the selection of the best models for each category. And then there is a final model that compares models and assess event class. And this is the structure I used for the data challenge. Okay, and of course, a final model that generates plots. Just a few details about all models. So for data preprocessing, so I want to stress that the RT model works in a completely unattended way. So it is designed to work for real-time modeling without any human intervention. So I don't set anything for the specific events. And this is the way I used also for the data challenge, because my purpose was to test the possibility to use this a platform like this for a completely unattended modeling on very large scales without any human intervention. So in any case, when you input, when you take your data, of course you need to do some preprocessing to assess the real the actual scatter of the data set. Then, since there are many data points, you don't want to use the 40,000 data points for the to make a 2-hour calculation. So points are classified by their significance. In particular, points that are very far from the peaks are given a very low significance. And so the data points are rebinned according to their significance. In practice, points that are very far from the peak, just on the baseline, they are just rebinned to give one significant data point to take into account for the baseline. So in the case of the data challenge, I went down from 40,000 points to 4,000 data points that were actually useful to characterize the light curves. And this is an example of how it worked. For example, this was the season in which we had the main event occurring, and then all the points outside the main season were very strongly rebinned. Okay, now second step is to set initial conditions for fitting. So we have to identify the peaks, and the idea now is to use this SP-line approximation. So in practice, I approximated the light curve with the SP-line until all residuals are less than 5 sigma, and then I can identify peaks within using this SP-line. And the two most prominent peaks are selected. In case there is only one peak, then the maximal asymmetry is used as a second peak. And this is so this is an example on one where this is not a W-first data challenge event. So this is 1434, and so if you approximate iteratively with the SP-line, this is what you get. And then this is useful to identify the most prominent peaks. Once you have the most prominent peaks, the idea is to match them to the peaks of a library of template light curves, following the approach by the Stefan and Mao, a very old paper many years ago. And so once you have the identified peaks in the data, you match with the template, and then you have the initial conditions for fitting. So I started 244 fits actually using these template light curves, and so I checked for all of them. And the fitting algorithm is a simple Levenberg-Marquardt downhill method. So, but in order to enlarge the search and jump out of local minima, the fit is run 5 times or a number of times, filling the first minima found with the bumper, with the penalty function, so that the second run will eventually find another minimum and so on. Okay, so as for the simple models, PSPL, ESPL, and binary source, then the fit takes just few seconds to explore all possible all possibilities, while binary lens fixed, of course, take most of the time. I told you that the 7 parameters for the static binary links are taken from the templates and from the matching with the peaks in the light curves. Then the search for higher orders in the current versions start from 0 values, so 0 parallax and so on. So once the best static models are found, then I search for the possible higher order effects. Okay, once I find a lot of possible models, so then I have to select the best few models. And so for each model, I can estimate uncertainty using the Fisher matrix inversion. And then if I have models with the uncertainty ellipsoids that overlap each other, I just take the better model, and the other one is discarded. Now, how many models should we retain as possible good models for the fit? Well, it's difficult to say, and many proposals have been made in several years. So these chi-square thresholds, 200, 100, whatever. So the idea for the purpose of the data challenge was to take something that had some any statistical foundation. So if you consider the original chi-square distribution, actually the chi-square distribution has you can identify a sigma threshold on the chi-square distribution, and this comes analytically from the study of the chi-square distribution. So in the case of the number of data points, which is 4,000, this threshold just happens to be 89 in delta chi-square, in terms of delta chi-square. So this has something to do with statistics, so it's good to take something that has some statistical meaning. Now, and note that error bars are normalized so as to have the chi-square equal to n for the best model in each category. Okay, now for the final classification I used in the data challenge, the first thing I had to check is that whether my best model was good enough. And so in the end, I took a threshold of a chi-square greater than 2n to say that my modeling has failed. And so in that case, I made a second run as described in the next slide. So if another thing I did, it was to say, okay, the light curve is compatible with flat. So if the delta chi-square from my best model and the flat line is less than 3 sigma chi, so the 89 delta chi-square I said in the previous slide, then the light curve was classified as flat. So it was compatible with the flat light curve. For all other models, instead, of course, you can always get a very slight improvement, including a larger number of parameters. But at some point, the delta chi-square you get by adding a parameter, of course, it doesn't mean that you have an evidence for that parameters to being measured. So in all cases, I identified nested models as models that can be for which you can identify a hierarchy, a clear hierarchy. And for these cases, you can apply so-called Wilks theorem. So in the Wilks theorem states that the evidence for an alternative model adding some number of parameters, n parameters, versus the null hypothesis is tracked by the chi-square distribution with m degrees of freedom. And so this defines a threshold. So if I want a 5 sigma evidence for the alternative hypothesis to improve with respect to the null hypothesis, then for 2 more parameters, the threshold is 40 in the delta chi-squares. For example, this if you want to claim evidence for the parallax model, this should be the correct threshold. And then for 3 parameters, 43.5, and so on and so forth with other, all the other thresholds. So in the end, this provides a criterion to say, okay, then I classify this event as a static binary model or a binary model with parallax or with orbital motion or whatever. In the end, for the models that cannot be nested, for example, binary lens versus binary source, in this case, the Wilks theorem cannot be applied, and in that case, I retain models that are within the previous threshold that I defined, so the famous 89 points in delta chi-square. As for failed models, so in the cases which I didn't find a good model with the first run, I made a second modeling run without static models. So I started with the same templates, but not looking for the static binary solutions, but looking for solutions including paradox from the very beginning. Because in most cases, the failure was due to strong higher order effects that cannot be considered as a small perturbation to a static binary models. So in that case, you have to include the paradox from the very beginning. Okay, and so if I couldn't find any model, the event is classified as variable. So this is just a flow a flow chart of all the algorithm, but I ran out of time, so I go very fast. It's just a summary of what I explained before. So this is a table with all the classes of events that I found in the data challenge. And so I already knew that there were some events that were misclassified, but I didn't touch the final result because I wanted to just to make a test on my code, a really blind test on my code to see whether it could find it was efficient in finding good solutions. This is just a distribution of the fitting time, so I can skip it. And so, in the end, it was comfortable to say that this number of events took a reasonable amount of time, and so it is possible to scale the existing software to WFirst with just by adding a suitable number of workstations. So just 4 or 5 workstations would do a good job in a reasonable amount of time for all the events that are predicted to come out with from WFirst. And of course, there are special events that will require particular attention, such as multiple lenses, binary source and binary lens. And so, of course, this should come out from the failed models, and someone should take care of that. Okay, and I think that's all.
Okay, thank you very much.